Okay, then welcome everyone. Part of you might know me. I've occasionally I attended a journal club, but we also talked with Dion. I was at NeurIPS last year to present my paper. It was called APEBench. APE stands for Autoregressive PDE emulators, and is a benchmark suite for the how neural networks can be used to predict spatial temporal phenomena. I will start a bit general, but then it gets more specific. So what does it mean to predict, or what are spatial temporal drift phenomena in the first place? I hope that this goes through with the Zoom recording, that there is a video. So this is about predicting physical phenomena that can reside in 1D, 2D, and 3D with an additional time axis. And typically, if you would do this on a first principle based approach, something you would find in scientific computing for engineering applications or general science or in computer graphics, a first principle based approach starts with a model of your underlying phenomenon. Most typically, this would be a partial differential equation that could also include some constitutive laws. And then in order to simulate this problem, you would apply some symbolic manipulation to this equation according to your discretization scheme, like a finite element method, and eventually implement it into the computer. And since we are talking about time-dependent problems, this usually gives you some time-stepping operator that would advance your state and time. And then in order to produce trajectories, you need a point to kickstart it. And this is like an initial state. And in the easiest case, for instance, you could have some superimposed sine waves in one dimension, which you would discretize on your representation that your operator is defined for. And then, of course, the process of producing trajectories is an inherently sequential one. So you will start at your initial frame, which is now encoded in a color, apply your simulation operator, get to the next state, then apply it again, and so on and so forth. And here you also see the intrinsic property of the advection equation as a simple example, which has like this initial condition moving over the domain. And of course, you would continue with that, not just like 5 frames, but hundreds or thousands of frames, very long time dependencies. And if we were to stack it a bit differently, we would see this spatial temporal plot. And this is essentially what autoregressive or spatial temporal simulation is usually about, let it be in 1D, 2D, 3D, or also on more complicated geometries. Autoregressive emulation now means that we want to replicate the behavior of this numerical time stepper with a neural network. And this neural network should have the same signature as this numerical time stepper. So meaning that it is also a first order Markovian process, taking one state and mapping it to the next. The reason why we want to do this could be plenty. So a pragmatic reason would, of course, be that we would want to find something which is more efficient than a numerical simulator, but it's, of course, very hard to achieve. The goal of APEBench, I think, is more academic, like understanding how these neural emulators learn, what kind of constraints they inherit from their numerical counterpart, and what different architectures do. So the task is about training these neural emulators with the help of the classical simulators. How would you do that? Well, you create a bunch of data. So this is the data trajectory we've seen before. You could vary the initial condition and create another trajectory. Usually you would do more, for instance, 3, but usually a lot of them. And then based on this data set, you will try to inject this knowledge via the classical deep learning optimization into the neural emulator. The most classical approach for that would be one-step supervised learning. That means like taking, for example, only 3 different trajectories. We would sample windows of length of 2 out of the trajectories and across time. So for instance, here I sampled 4 windows out of these 3 trajectories. And then these windows will be split into input and target. And then we have a classical supervised deep learning problem. So we will take the inputs, apply the network, compute the loss, and then backpropagate into the parameter space and iteratively update the weights. What I find interesting about that is that we do a one-step supervised prediction, which is a bit different from what we might want the emulator to do in inference. So in inference, we wanted to run autoregressively for plenty of time steps. And that's, of course, a different task than only training one step into the future. So in these classical one-step supervised scenarios, there's this typical discrepancy. You do one-step training, but eventually you want to do autoregressive rollout. And autoregressive rollout is quite complicated. It's not only complicated for emulators, it's also complicated for classical approaches with regards to long-term accuracy, how errors compound, and long-term stability if errors explode. Or in general, one could say that in more deep learning terminology, we are after temporal generalization. And what I find very interesting, and which has been fascinating me ever since I worked on APEBench, is that despite this obvious discrepancy, this works surprisingly well. So if you train a network with one-step supervised prediction, so what you see here is a network being trained with training loss, and then here it's very oscillatory, it will get better. You see how the network predicts spatiotemporally over the optimization. And in the bottom, you will see an error rollout. I will repeat this animation. And then essentially you see that after the training, the network does a fairly decent job at predicting the advection equation. And this is special because it never learned to do it autoregressively. It only learned a one-step prediction, albeit of course across multiple trajectories and multiple time steps, but it really learned to temporally generalize. This is about the essence of like autoregressive emulation. You find it in different flavors in various works. Now, APEBench is about building a benchmark suite around autoregressive emulation. So let's look at the typical pipeline more abstractly than what we did so far. So this does not work. Yeah. As said before, we usually start at PDE and some form of a distribution of an initial state, which we translate into a discrete representation because we work on a computer, and then autoregressively roll it out into a trajectory. And typically, you would repeat the process, use different PDEs, different samples from the initial condition distribution, and create a data set of trajectories. This would be split into a training subsection, and then a typical benchmark architecture would also ship some architectures, which you would initialize, and then with an objective like the aforementioned one-step supervised training, you would produce a trained artifact. The data trajectories then might also contain a holdout test data set together with a metric function. You can then benchmark your model. And that's, I guess, is a fairly typical approach if you want to train these models synthetically and not via residuum-based losses. And the difficulty I find in this approach is that, or typically when you look at datasets and benchmark papers, is that the interface between whoever creates the dataset and whoever uses the dataset is in these data trajectories. And they are pre-computed and fixed. So here I mentioned 10 to 1,000 gigabytes, but I think maybe you've heard of the well dataset from NeurIPS, which was on the order of 10 terabytes to hundreds of terabytes. And that's, of course, a large amount. And I think like handling these data, especially if you are after more core questions, like what APEBench is about, is a bit of a pain. And especially, I find it interesting in like really getting the entire experimental loop from data generation to training to evaluation as short as possible to make the idea of hypothesis testing way faster than and make it able for these smaller scale problems. Okay. Of course, since most of these dataset publications would then have the dataset fixed, there's of course a good reason why they do this, because the data generation process is slow and therefore needs to be done offline. The disadvantage when doing so is that typically the user does not have access, or at least not directly, to the numerical solver, which is like what I call the time stepper here. So they couldn't, for instance, benchmark neural hybrid approaches, like what we, for instance, saw in the neural GCM paper, or they could not do any differentiable physics during training, which would require the numerical simulator. And another disadvantage, often when this is the interface, is that it's not 100% clear what the underlying PDE is. Oftentimes there's good metadata, but sometimes some information, for instance, with respect to the numerical discretization choices, must be is lacking. Now, what is the difference with APEBench? And the key innovation with APEBench, or I would say the key contribution with APEBench, is that we build a fast numerical simulator. And this is basically the core of the entire benchmark suite, and we build everything around that. And I think this should also highlight that we don't have this two nature, because a lot of the research is just based on the data sets and just on the downstream deep learning, but never on the holistic pipeline. So the advantage of having this fast numerical simulator is that we can procedurally generate all training data. This, of course, comes with the caveat that we have a very constrained setting, but still I find that this allows for many interesting PDEs that give interesting insights into autoregressive neural emulation. Another advantage of the time stepper is that we can build hybrid approaches, or we can benchmark hybrid approaches, and we have differentiable physics available during training. And another contribution we made, I also want to highlight, is a way to reduce or find a reduced interface describing what particular PDE is being emulated. And I will present that in a second. Let's first talk about this fast time stepper. So it is based on Fourier pseudospectral ETDRK methods. ETD stands for exponential time differencing and RK for Runge-Kutta. And they work on uniform Cartesian grids with periodic boundary conditions. It's of course a bummer. It is like not the most general setting, but it still covers a wide range of problems. And they work like in 1D, 2D, and 3D. And they work specifically well for so-called semi-linear PDEs. That means that if you have a PDE with a linear differential operator and the nonlinear differential operator, semi-linear means that the difficulty of integration comes from the linear part and not from the nonlinear part. That, for instance, covers the Kuramoto-Sivashinsky equation or the Navier-Stokes equation at low Reynolds numbers. It does not cover the NS equation at high Reynolds numbers. And those equations are then discretized. I don't want to go too much into details. The schemes by itself, I think, are fairly easy to understand, and I spent a lot of effort writing it down in the appendix. But the cool thing is, and I think one contributor of the performance is that all of it is implemented in JAX. And this is also like the entire benchmark is implemented in JAX, so that all works nicely together. And then the second contribution I want to talk about is these PDE identifiers. We also called it a difficulty-based interface. It might not be the ideal name, but at least it gives a bit of a hint what it's about. Let me give you a motivation. So when you look at the semi-linear PDEs, for instance, in 1D, they contain a nonlinearity. So for instance, here I chose the convection nonlinearity, which is scaled by this coefficient here. And then I have some linear terms or linear derivatives scaled with respective coefficients. If you were to communicate what kind of PDE you're simulating or emulating, you would collect these coefficients. You would collect some other choices, for instance, which spatial dimension, how large the domain is, the resolution, time step size, and of course, to really precisely create a setting that could reproduce the data trajectories, you would of course also need to define the numerics. That means, for instance, which numerical schema you're using, but also some minor choices within the numerical scheme. The problem with that is that it's, of course, a wide set of metadata. And oftentimes, when you see data sets, it's a bit lacking, especially also on the numerics end. And so what we did is we reparameterized this. So first of all, we by default use a second order ETDRK method. The ETDRK method has the advantage, first of all, it's fairly stable if the problem is semi-linear. But on top, the internal numerics choices of ETDRK methods are fairly well behaved. So that usually X's out the numerics component. And then we use the first two set of parameters and reparameterize them, effectively removing two components here, and then leaving us with what we call delta and gamma values. So they are still associated with their respective components in the PDE. So for instance, gamma 2 is associated with a diffusion component. Gamma 1 is associated with an advection component. And the reason we did that is multiple. So first of all, we get smaller number of parameters. That's very nice because, for instance, let's say you had an advection PDE, then you would only need to communicate the gamma 1 value and D and N. Or if you just say I'm always 1D, then it's just two values, gamma 1 and N, which is a nice way to really say this is my emulation setting. The other advantage is that all of these values have reasonable orders of magnitude. So they range from 0.01 to 100, which I think if you've ever created data sets which had like parameters and you wanted to sample them. That's always a bit of a mess if you have to logarithmically sample or something like this. And the other advantage is that they have nice interpretations. So for instance, so all of these gamma values correspond to stability conditions of the most compact finite difference schemes. We will see that more in a second as well. I also have a small animation that shows what it means with these gamma values. So here we have a gamma 2, gamma 3, and delta 1 being non-zero. And then we basically span a three-dimensional space. Here I also fixed n resolution and spatial dimension. But with that, we can smoothly interpolate between diffusion, Burgers, Korteweg diffees, and so on and so forth. And of course, most importantly, I mean, we call them difficulty for a reason, because the higher the value, the more faster the dynamics, and therefore also the harder the emulation. And I think this is quite important, because otherwise, typically people say we are, for instance, emulating Burgers or whatever equation, but of course you can have fast-moving Burgers or slow-moving Burgers, and as such, the emulation is differently difficult. Okay, so in general, concluding for this APEBench, what are these possible axes of investigation? So with APEBench, you could vary the PDE, both the kind of PDE by changing which difficulty values are non-zero, but then also changing their concrete values, making it more or less difficult, or just using the default settings. Then, of course, obviously, you can change the neural architecture. I guess that's the most default axis of investigation that you find in benchmarks. You can do the learning methodology. We didn't talk much about that because of time constraint, but you can, of course, do more than just one-step training. You could do unrolled training. And you could have a different learning goal, like instead of doing prediction, doing a null hybrid correction approach that combines a solver component and a neural component, which, as far as I'm aware, this is the first benchmark where you could do that. And of course, most importantly, this is all wrapped like in a setting that you do seed statistics by default to enable hypothesis testing. This concludes APEBench, the design a bit. I want to present one experiment which I find interesting to show you what kind of experiments are possible. And this is again about the advection emulation. I know it's a bit of a boring thing, but I find there is so much to learn about advection emulation. And here we see this rollout metric. So on the x-axis, we see like autoregressive inference rollout. And then on the y, we have some error metric. And then essentially we compare different architectures. Here first, I looked at exclusively feed-forward convolutional architectures and varied their depth. This means how many hidden layers are stacked. And for a ConvNet, this essentially also means what is the effective receptive field. And now we have an interesting relation to these gamma identifiers, because here in the advection occasion, they can be interpreted as the CFL number. And of course, with explicit finite difference schemes, you have it that you need the CFL number to be smaller than 1. But that's, of course, because they often tend to have limited receptive fields. And so what we see here is that if we choose a convolution depth of 0, that just means we only have one convolution. It's still able to learn the advection. So it is stable because the growth is not exponential, but linear. But it's worse, of course, than if we had more depth. And the interesting thing here to note is that we see the similarity between convolutional architectures and finite difference methods, and that they to some extent also inherit the limitations we see with finite difference methods. Then let's bump up an axis of investigation. Now we can vary the PDE. We will still keep advection, but we will increase the advection difficulty. So here we increase the CFL number. And if we increase it at 2.5, we see that 0 is really insufficient. It's up here. So it is growing exponentially. So it is diverging. It's unstable. So is also convolution depth 1, which also has insufficient receptive field. Surprisingly, here also convolution depth 2, albeit being stable in the beginning, is also exploding. And only the largest ConvNet is stable in this regard. But of course, this is giving some ideas of how one can interpret these convolutional architectures. Of course, the more classical benchmark thing to do is to compare classes of architectures. So we could now just say, well, we keep the largest ConvNet and now look at different classes of architectures. So instead, here we have 3 classes. convolutions and ResNets are like what I would call local convolution architectures. They don't use any mechanism to increase their receptive field. We have a UNet and the dilated ResNets. They use two different kinds of methods to increase their receptive field. And we have the FNO as a Fourier spectral architecture. And we see that for the low difficulties, the local convolutional architectures work best, and they get worse, and then ultimately almost don't work anymore at the highest difficulty. On the other hand, for the long-range convolutional architectures, we see that they perform the worst on the low difficulty setting. That's because they have wide receptive field. They spend a lot of parameters on unnecessary receptive field because it's such a slow-moving phenomenon that doesn't need wide receptive field. But on the other hand, they of course benefit if the dynamics are moving fast. What you also see here is that the FNO performance is almost agnostic to the difficulty. And that's of course because here we have a linear PDE on a periodic boundary condition that is solved with a Fourier spectral method. And now we throw a Fourier spectral emulator in it. That's of course a prime setting for the FNO. And that's also to some extent caused by the fact that FNO's performance is not limited by receptive field, but rather by the spectrum of the solution. And here the FNO has sufficient active modes and can have infinite receptive field. So it's it is in that sense the best choice. Okay, that's to conclude this experiment. We can talk more about that in the question section. In general, what can APEBench be used for? So we can do studies. This is what I presented to you. That's a way to understand neural emulators better and how to train them. And what I really like to do is see the similarities to classical numerical methods. Then, of course, we can do benchmarking. I mean, it's a benchmark, right? So if you have a new architecture, this can be benchmarked against like the, let's say, default architectures. And of course, I would say for the first time, please correct me if I'm wrong, this is a benchmark that supports neural hybrid approaches. So for instance, you propose a new architecture and don't want to have it on a full prediction setup, but instead do it like on a correction setup against like an unstable solver, for instance, that can be benchmarked. It can be used for data generation. This is specifically important, I think, for these trends on foundation models, because I think the PDE identifiers with the difficulty interface are especially suited for such tasks because they allow such nice sampling within their space. First of all, the space is reduced, and then those have like reasonable orders of magnitude. And I've already seen it is used for some foundation model projects. So I guess it can be a good choice in that regard. Okay, overall, I want to conclude. So what is APEBench about? So first of all, it's check-space. That I would say to some extent is also a novelty because most of the DNB papers you've seen over the past years mostly relied on PyTorch. It has this fast reference simulator that's based on spectral methods. That is very cool because it, first of all, gives procedural data generation in seconds. So you generate gigabytes of data in seconds. It is like crazily fast. I think it's still unbelievable for me that you can generate the data so quickly. And now that I'm working on other projects where data generation is orders of magnitude slower, I'm always looking back to these, let's say in quotation marks, toy settings. This reference simulator also gives you differentiable physics, which is very cool, and allows for benchmarking stuff that hasn't been able to benchmark, at least not that easily before. We didn't talk how many PDEs. We claim like 46. I think counting PDEs is a bit hard, especially if we have this general interface. So there are definitely more than 46, depending on how you combine the coefficients, but just to give it a number. Then we implemented a lot of emulator architectures. So all the architectres you see are re-implemented. They're mostly inspired by PDE Arena. But of course, I think this could also help like kickstart more emulator research in JAX now that these architectures are available. We didn't talk much about unroll training for the sake of time, but this is also supported in various flavors, also with differentiable physics. We'd have this neural hybrid emulation. And also something I did not talk, but you saw my co-author Simon wrote an amazing volume renderer, which works on WebGPU. And I think even if you don't work much on Cartesian data, I think this is a very nice tool if you can remap your data to Cartesian. I think it's so cool because it directly integrates into Jupyter. Yeah, that's very nice. And I think ultimately what I loved about doing APEBench, and I'm still using it for, and I'm still trying to find new studies that show more similarities between emulators and classical numerical methods. I think this is important for multiple reasons. So first of all, we can learn a lot from numerical methods. And on the other hand, I also think that by a lot of inductive biases we've been developing over the past years, we are to some extent just resembling numerical methods. And it's interesting to see that experimentally, that these neural emulators that are built with specific inductive biases, like convolutional networks, will of course inherit the limitation of their classical numerical counterpart. Okay, that's it for my presentation. APEBench is installable via pip, and that's the cool thing. So it's a megabyte of installation, and you can generate hundreds of gigabytes of data. So that's a good deal, I guess. Thanks so much for listening, and I'm happy to take your questions.